due to the formation of ethanol water azeotrope, the production of ethanol with purities in excess of 95% is impossible in normal distillation operations and requires the use of azeotropic and extractive distillation and the use of entrainers such as cyclohexane and benzene. Azeotropic and extractive distillation are energy intensive, and a practical solution for energy reduction is to have a hybrid distillation membrane construct in which the top product from the distillation unit is fed to a membrane pervaporation device with a thin layer of membrane such as LTA4A zeolite. Water vapor permeates preferentially through such membrane constructs, and the permeate, which is rich in water, is recycled back to the distillation column, whereas the retentate is drawn off as a product with purities, say, in excess of 99.5% ethanol. For background details, I refer you to my paper in Journal of Membrane Science 2024. The ideal choice of membrane materials for use in membrane pervaporation units are shown here. DDR zeolite that consists of cages of 280 cubic angstrom separated by narrow windows with apertures of the order of 4 angstrom. Chabazite with cages of 316 cubic angstrom separated again by narrow windows of about 4 angstrom in size. ZIF, which has larger cages separated by windows of about 3.3 angstrom, and LTA4A zeolite that consists of cages of 743 cubic angstrom separated by narrow 4 angstrom windows. A common characteristic of all such materials is that the membrane permeation selectivity is favorable to water pervaporation due to the fact that the diffusion selectivity favors water and the adsorption selectivity also favors water for feed mixtures that contain less than about 5% water. This is not an obvious conclusion, but I'd like to elaborate on that. Due to hydrogen bonding between water and ethanol, the absorption of water is significantly strengthened due to its clustering with partner ethanol molecules. An important corollary of this hydrogen bonding phenomena is that the mixture adsorption equilibrium is strongly non-ideal, as I have discussed in this paper in fluid phase equilibria. To demonstrate the thermodynamic non-idealities for mixed water-ethanol mixture adsorption, we conducted configurational bias Monte Carlo simulations for mixtures of water and ethanol with a total fugacity of 10 kilopascal and varying composition of water in the bulk phase mixture, varying from 0 to unity. The blue triangles are the CBMC simulation data for water ethanol adsorption selectivity as a function of mole fraction of water in the bulk mixture. We see that for concentrations of water in the bulk mixture less than about 10%, the adsorption is strongly in favor of water. When the feed mixture becomes increasingly richer in water, the adsorption selectivity is in favor of ethanol. So we have the formation of an water ethanol azeotrope in the adsorbed phase. The CBMC data can be fitted with the real adsorbed solution theory with introduction of activity coefficients in the adsorbed phase mixture. If we use the ideal adsorbed solution theory, this anticipates that the water ethanol adsorption selectivity is always in favor of ethanol and no selectivity reversal is anticipated. This has been discussed in my paper in 2025 in fluid phase equilibria. These are the results for DDR zeolite. For chabazite, we have a analogous situation. For small mole fractions of water in the bulk phase mixture, the adsorption selectivity is in favor of water, and as the water mole fraction in the feed mixture increases, the selectivity reverses in favor of ethanol. The RAST calculations with fitted activity coefficients using the NRTL model are shown by the continuous solid line. The IAST anticipates that the selectivity increases in favor of water with increasing mole fraction of water in the adsorbed phase. This is opposite to the trend dictated by CBMC simulations. For ZIF8, the CBMC data again shows that the water ethanol selectivity decreases and becomes increasingly in favor of ethanol as the mole fraction of water in the bulk fluid phase mixture increases. In all cases, we see that the IAST underestimates the water ethanol selectivity at low concentrations of water in the bulk phase mixture. This is the concentration range of importance in water ethanol membrane permeation devices. Let's examine how the membrane permeation works in favor of water. We can set up a membrane pervaporation model as described in my Journal of Membrane Science in 2024, the membrane pervaporation units consists of a thin porous crystalline layer consisting of, say, DDR zeolite or Chabasite zeolite or ZIF. Typically, the thickness of the membrane layer is 50 micrometers. The upstream compartment contains the feed mixture, which is typically rich in ethanol, say about 95% ethanol, and the downstream compartment is subject to deep vacuum. The upstream face of the membrane is in equilibrium with the bulk phase mixture, and the component loadings for water and ethanol can be determined using the real adsorbed solution theory. The adsorbed phase mixture diffuses across the membrane, and for description of the mixture diffusion within the microporous crystalline layer, we use the Maxwell-Stefan formulation, taking due account of thermodynamic coupling effects as described in detail in my Journal of Membrane Science paper. The membrane pervaporation model has been applied to calculate the fluxes and permeation selectivities for water ethanol mixtures across DDR, Chabasite, and ZIF membranes. The water ethanol permeation selectivity calculations are shown here for DDR, where the permeation selectivity calculated using the RAST model taking due account of thermodynamic non-idealities is shown by the continuous solid line, and the dashed lines are the corresponding IAST model calculations. And we note that the permeation selectivity in favor of water is about a factor 5 higher when the RAST is used to model the water ethanol membrane pervaporation. The same story holds for a Chabasite membrane. The permeation selectivity predicted by the RAST model for membrane pervaporation is significantly higher by about a factor 5 for mole fractions of the feed mixture smaller than about 10% as compared to the IAST predictions of the water ethanol permeation selectivity. For ZIF, the RAST calculations are about a factor 2 higher than the calculations based on the IAST for mixture adsorption equilibrium between the upstream compartment and the upstream face of the membrane layer. The details of these calculations are provided in my Journal of Membrane Science paper. See also my paper in fluid phase equilibrium. Watch also my presentations on water ethanol pervaporation and the real adsorbed solution theory on my YouTube channel. The important takeaway message from this presentation is that for modeling of membrane pervaporation units, the accounting of thermodynamic non-idealities is of vital importance. Ignore thermodynamic non-idealities at your own peril.